So I'm going to call this one a bonus example. After the last one we did, you might not need another example, but if you're looking for more practice, this is not a bad one to have a look at. So we have a sinusoidal wave. It has an amplitude of 1.5 centimeters and a frequency of 150 hertz. It's traveling at 300 meters per second in the negative x direction. At t equals 0, the point at x equals 1.5 meters is on a trough, so it's at a lowest point. So let's just do a little bit of a sketch. So let's see. So our wave looks something like this. It's traveling to the left, so the wave speed v is right there, and the amplitude is up this way. We can make a list of the things that we know. So the amplitude A is 1.5 centimeters. The frequency F is 150 hertz. The wave speed V is 300 meters per second. Careful with signs here. Just because it's traveling left doesn't mean you make your wave speed negative. This is a speed. It's a scalar, so this doesn't have a sign. At t equals 0, so if t equals 0 and x equals 1.5 meters, it says that the wave is on a trough. That means our value of d at x equals 1.5 meters and t equals 0 is negative of the amplitude. Okay, so it's at minus 1.5 centimeters. So let's get into what the question is asking for. Determine or write down the values of amplitude, wave speed, wavelength, wave number, frequency, angular frequency period, and phase constant. Some of these are going to be simple, they're just given. Some of these are going to require a little bit of work, but let's get started all the same. So the first one, the value of amplitude A, that one's easy, it's 1.5 centimeters. The wave speed V, 300 meters per second. Wavelength lambda, let's see, we don't know lambda. Is there anything else we do know though? Let's see, we know the frequency and we know the speed, so that tells me we could find the wavelength. Go down on a new line for that one. So we want the wavelength. We know V equals F lambda. So lambda equals V over F. F is a number we know and we were asked for. We'll write that down after we find K. F is equal to 150 hertz. So lambda is V over F, 300 meters per second, divided by 150 hertz. Remember, hertz is just seconds to the minus 1. Gives us a wavelength of 2.00 meters. So A is done, V is done, lambda is done, F is done. Next we want to find K. Remember, K is the wave number. It's 2 pi over lambda. So 2 pi over 2 meters is going to give us 3.14 radians per meter. The radians comes from pi being in radians. It's considered dimensionless. Radians is not really a unit, so you could also just say that K is meters to the minus 1. That's also acceptable. Okay, K is done. Omega, we can find omega from our F because we know omega is 2 pi times F. So 2 pi times 150 hertz gives us 942 radians per second. Again, radians are considered dimensionless, so you can just say seconds to the minus 1 if you wish. That's omega done. Next we need period. Well, we know period is 1 over frequency. So 1 over 150 hertz. Put that through the calculator, you should get 0.00667 seconds, or 6.67 milliseconds if you prefer, that's okay. Okay, these guys, they were a piece of cake. This one, phi naught, that one's not so easy. How do you find the phase constant? If you're not sure right off the bat, and these do take a little bit of work and a little bit of practice, why don't we write down the equation of motion for the wave? So let's write down what the equation of motion is. Let's ask, do we know anything to plug in there? And can that let us find our phase constant? So So let's start with that. So the equation of motion is d of x and t is equal to a times sine. Let's write down the general function first. Kx plus or minus omega t plus phi naught. Plus or minus is definitely important. We use plus if the wave moves left. We use minus if the wave moves right. Our wave is moving to the left, so we need to use the plus. So let's fill in the things that we know. We know that if x is 1.5 and t is 0, the height of the wave, d, is minus the amplitude, or minus 1.5. So there's stuff that we know. So let's fill in the things that we know, and then let's use those things to find our phase constant, phi naught. So d of x and t is minus amplitude, minus 1.50 centimeters, because it says the wave is on a trough. That's the lowest point, so it's a negative amplitude, equals the amplitude A, 1.50 centimeters, times the sine of k. K is 3.14, times x. X is 1.5, plus omega. Omega was 942, times our time, which is 0, plus phi naught. And our brackets are closed. Okay, this whole term's gone. Let's simplify this a little bit more. Minus 1.5 divided by 1.5 is going to give us minus 1. So you divide both sides by 1.5. Then the centimeters cancel out. And that's going to be equal to the sine. 3.14 times 1.5 is 4.71. That guy is 0 plus phi naught. So we're getting somewhere here now. In this equation, we see that the only thing we don't know is phi naught. So let's start to solve for this. We have to take the inverse sine of both sides. So the inverse sine of the sine of 4.71 plus phi naught is 4.71 plus phi naught. So the inverse sine of a sine leaves us with just the argument. That's going to be equal to the inverse sine of minus 1. So now we have to find the inverse sine of minus 1. And I'm going to say when you come to these problems, you should choose wisely. Okay, that's really very important. This example, this bonus one, I've picked this one as pretty straightforward. We are going to get to harder examples where that wise choice might be even tougher to think about. So we'll start simple and we'll ramp it up. So I'm going to write down here, choose wisely. Now let's get into what do I mean by choose wisely. Think about the unit circle. I'm going to guess most of you guys did the unit circle in your high school math. So here's our unit circle. We're trying to find the inverse sine of minus 1. So that's down here on this part. So the inverse sine of minus 1, and this is what you would get if you hauled out your calculator. If you grab your calculator, I don't know if I have mine handy. I don't either. So if you grab your calculator, you set it to radians mode, you do the inverse sine of minus 1, the answer you're going to get is minus pi over 2. And that answer is 100% correct. The inverse sine of minus 1 is minus pi over 2. You can tell that that's true because if you do sine of minus pi over 2, you're going to get minus 1 for your answer. So that's okay, that's true. But if I put minus pi over 2 here and I solve for phi naught, that's going to give me a negative value of my phase constant. That's not really wrong, but I'm going to say it's not typical. We don't traditionally represent phi naught as a negative answer like that, as such a big negative answer. Normally it's a positive answer between 0 and 2 pi. So that would give phi naught negative. I'm going to say that that's not typical. Okay, I'm definitely not going to say it's wrong, but it's not the usual way we answer this. So if that's not the typical way, what is the typical way? What are you supposed to do if the calculator doesn't tell you the right answer? My goodness, I misspelled calculator terribly. There we go, that's better. So if you look at this angle, 3 pi over 2, if you do the sine of 3 pi over 2, that also gives minus 1. Okay, so then this answer is also valid. So the inverse sine of minus 1 can be minus pi over 2, but it can also equal 3 pi over 2. And that's because the sine of 3 pi over 2 is minus 1. So both of these answers are valid. This one doesn't give the typical result, so let's try this one. So 4.71 plus phi naught equals 3 pi over 2. I'll solve for phi naught by subtracting 4.71 from 3 pi over 2. That gives 0. So 4.71 is 3 pi over 2. So our phase constant in this case is 0. Had we moved on with this, if we had said that our inverse sine of minus 1 was minus pi over 2, we would have gotten a phase constant for minus 2 pi. You might have seen at that point that you should pick 0 instead. But anyway, here's typically how you would go through that process. You look at what your both results are, and you pick the one that gives you the phase angle between 0 and 2 pi. Okay, there's part A all done. Let's go to part B. Write the equation of motion for the wave as it travels. That question says, write down this equation, but plug in all the numbers that you know. That's what that question is asking you to do. So I'll grab a fresh sheet of paper and we'll write down that, and we'll look back at this first slide as we go. So part B is write the equation of motion. So as a reminder, I'll write the general form here. d of xt is amplitude times sine kx plus, because the wave moves to the left, omega times t plus phi naught. Now we'll stick in the numbers that we know. d of xt is equal to. Come back here to our list. A is our amplitude, 1.5 centimeters. You can leave it in centimeters or you can convert to meters. Doesn't matter as long as you're careful with your units when you do your calculations. Times sine of k. K was 3.14 radians per meter. You can put in your units here or not, up to you. Plus omega times t. Omega was 942 radians per second. And then our phase constant phi naught we saw was 0, so we can just close our brackets. Then part C says draw a picture of the wave at t equals 0. So for part C, we put in t equals 0, which tells us that d of x and 0. So this means we're drawing a picture of the wave at a fixed time. So this is a snapshot graph. So it's the whole length of the wave at one moment in time. So d of x at time equals t is 1.50 centimeters times sine of 3.14 times x. So if we're going to do this guy, I'm going to hollow out a piece of graph paper just because it helps me draw things nicely. What am I going to put in on my graph? Well, if x equals 0, I want to try and find my starting point. X equals 0 says that d is equal to 1.50 centimeters times the sine of 0 is going to be 0. So my graph is going to start at 0. And then as my x get bigger, my d is going to get bigger, and my graph is going to repeat every wavelength because that's what happens in a snapshot graph. It repeats over a characteristic time. So it's going to repeat every wavelength. Our wavelength we found up here was 2 meters, so it's going to repeat every 2 meters. So, bring over my graph paper. So on my graph, this is my d of x at time equals 0. This is my x. My first point is at d equals 0. It goes to the amplitude at a quarter of a period, at a quarter of a wavelength, back to the equilibrium at a half of a wavelength, down to the negative amplitude at 3/4 of a wavelength, and back to equilibrium at the wavelength. So we get one full cycle, one full wavelength in a distance of 2 meters. So this is 2.0 meters, this is 1 meter, and in the middle here are 0.5s. Okay, so then my pattern repeats, get another wavelength, and that repeats over a distance of 1 wavelength. So over here is 4 meters, this is 3 meters, and then I can draw that as long as I care to. If you like drawing these on Excel or something, that's no problem, but it's always useful to be able to make a sketch of your graph. Okay, so that's the end of our first bonus example.